Hello, and good morning, good afternoon to everybody, and thank you for connecting to today's e-seminar. Today's e-seminar is Demystifying ICP-OES Spectral Connection Models, an explanation and implementation tutorial. One sec, just setting up the presentation here. So, before we get started, I'd like to go over a few items so you know how to participate in today's event. For the attendees unfamiliar with GoToWebinar, we've taken screenshots of the attendee interface. There are two ways in which you may have entered the webinar, either by downloading the application or using the web interface. On the right is the web version, on the left is the desktop version. The desktop application is shown here. On the left is the GoToWebinar viewer through which you'll view the presentation and maximize this to more easily view what is being presented. The right is the GoToWebinar control panel. You can ask questions, download handouts, and select audio mode. Note that the control panel will collapse automatically when not in use. To keep it open, you can click the View menu and uncheck Auto Hide Control Panel. Here's the web interface. The presentation will be shown in your browser window and will have the web-based control panel on the right side of your browser. This is where you can ask questions, open handout, and have it enter the full screen mode. You'll have the opportunity to submit text questions to today's presenter by typing your questions in the questions pane of the control panel. Web interface is shown on the left and desktop application on the right. Me sending your questions at any time during the presentation. We'll collect these and then address them during the Q&A session at the end of today's presentation. To hide and open the control panel for the desktop application, click on the orange button with the white arrow. I'd now like to introduce our speaker for today, Brady Froh. Brady is currently a field application scientist with Perkin, Elmer, based out of Pennsylvania. Before joining Perkin, Elmer, he spent nearly a decade as an analytical chemist, working primarily with ICP-OES and ICP-MS in contract and R&D laboratories. His experience includes trace and assay analysis of metallurgical samples, alloys, plastics, polymers, polymer additives, geological samples, specialty gases, food additives, enzymes, fuels, oils, and emission counts. Quite a list there, Brady. Brady has a Doctor of Science in Chemistry from Moravian College. And his contact information is there and will be at the end of his presentation. So to get today kicked off, I have a few polls just to quiz the audience here and just see where everybody's coming from. So for the first poll, I'd like to ask, what is your primary area of interest? We'll give about 60 seconds for this poll. Okay, well, thank you very much for voting. Looks like it's a decent mix of attendees from chemical to environmental analysis and some other sorts of research as well. And another quick poll here is, do you have an ICP-OES in your lab? A real simple yes or no type question. We'll give maybe 45 seconds for this one. Okay, we'll do a few more seconds here. All right. Well, thank you for voting. Yeah, so majority of people here do have an ICP-OES in their lab. That's great. So this will be a very applicable webinar for you. And one last question to understand if you're using interelement corrections or multi-component spectral fitting in your to deal with ICP-OES spectral interferences. Let's do about 45 seconds for that. Okay, give a couple more seconds here. Most people have voted. Okay, sure looks like it's a good mix. Obviously, the people without ICP-OES in lab wouldn't be applicable to you, but so about 50-50 approximately are using some sort of correction to deal with spectral interferences. Okay, that's excellent. Well, without further ado, I will hand it over to Brady and talk about the demystifying ICP-OES spectral correction models. Give me a sec and I'll pass it over to Brady here.
Thank you for the introduction. Hello everyone, thank you for attending today's webinar. I am Brady Frill, the Inorganic FAS for Pennsylvania and New Jersey. During this presentation, I'm going to describe the two choices for ICP-OES spectral interference correction models and detail how to implement them using statistics for ICP-OES software. Perkin Elmer is the global leader in ICP-OES instruments. We have a long history of innovation in atomic spectroscopy and ICP-OES, beginning with the introduction of the ICP-5000 in the 1970s. We have continued to improve and innovate all the way through the Optima series of ICP-OES up to our current models, the Avio 200 and Avio 500. A few of the key features of our current Avio series of ICP-OES. Both the Avio 200 and the Avio 500 offer superior performance while consuming approximately half the amount of argon as other ICP-OES systems, just 9 liters per minute for most applications. Since no copper helical coils are used, maintenance costs, consumable costs, and instrument downtime are greatly reduced. The vertical torch and sample introduction system design allowed the Avio series to be extremely compact, just 76 centimeters wide for the Avio 500 shown, maximizing the free bench space in your lab. Let's take a step farther back. What is an ICP-OES? What does ICP-OES mean? ICP, inductively coupled plasma, is the excitation source. It imparts energy into the atoms and ions present in the solution being aspirated into the plasma. Strictly speaking, a plasma is any form of matter that contains an appreciable fraction of electrons and positive ions in nearly equal numbers, in addition to atoms and neutral molecules. There are two characteristics of a plasma: that it conducts electricity and that it is affected by a magnetic field. The plasmas used for analytical atomic spectroscopy are highly energetic, ionized gases, usually argon. Plasma discharge is considerably hotter than flames and furnaces, and thus are used to dissociate almost any type of sample, as well as to excite and/or ionize the atoms for atomic and ionic emission. Once the excited ions exit the plasma, they cool and emit photons of light. This light is then separated by the optics and measured. This process is called optical emission spectroscopy. The inductively coupled plasma discharge used today for atomic emission spectroscopy is very much the same in appearance as the one designed in the early 1970s. Argon gas is directed through a torch consisting of concentric tubes made of quartz or some other suitable material as shown. Usually, a concentric copper coil called the load coil surrounds the top end of the torch and is connected to a radio frequency RF generator. When RF power is applied to the load coil, an alternating current moves back and forth within the coil or oscillates at a rate corresponding to the frequency of the generator. This RF oscillation of the current in the coils causes RF electric and magnetic fields to be set up in the area at the top of the torch. With argon gas being swirled through the torch, a spark is applied to the gas, causing some electrons to be stripped from their argon atoms. These electrons are then caught up in the magnetic field and accelerated by them. Adding energy to the electrons by use of a coil in this manner is known as inductive coupling. These high-energy electrons in turn collide with other argon atoms, stripping off still more electrons. This collisional ionization of the argon gas continues in a chain reaction, breaking down the gas into a plasma consisting of argon atoms, electrons, argon atoms, forming what is known as an inductively coupled plasma discharge. This ICP discharge is then sustained within the torch and load coil as RF energy is continually transferred to it through the inductive coupling process. Shown is a simplified overview of how ICP-OES instruments function. The argon plasma excites the atoms or ions that are being aspirated into it. This excitement is an electron being moved from a low-energy orbital to a higher-energy orbital. When the atoms or ions then exit the plasma, the electrons move back into the lower-energy orbital, and the excess energy they collected is emitted as photons of light. The optics then separate the emitted light into its characteristic wavelengths, which are converted to electrical signals by the detector which measures them. Perkin-Elmer's Avio series of ICP-OES instruments performs the inductive power coupling not with a copper load coil, but with our patented exclusive flat plate technology. Unlike traditional helical copper load coils, the flat plates require no maintenance and will not deteriorate with time. With reduced maintenance comes a greater amount of instrument uptime and lower consumable costs. The flat plate technology allows for the Avio series of instruments to operate at half the argon consumption of instruments with typical helical coil designs. The flat plate technology also allows a full power range from 1000 to 1500 watts in 1 watt increments and is quick to change regardless of viewing mode. It is fully customizable in the method on a wavelength by wavelength basis. Having the ability for increased plasma power can be helpful if attempting to quantify elements which are poor light emitters like selenium and cesium. Conversely, reduced plasma power can be useful for the quantifying of easily ionizable elements such as sodium and potassium. The spectral problems that may arise with ICP-OES analyses are spectral interferences. Spectral interferences are caused by unwanted light reaching the detector, typically caused by multiple elements emitting at similar wavelengths. This can be especially problematic for sample matrices containing large concentrations of inorganic elements. For example, look at the emission spectra for iron in the top right. Iron has over 800 emission lines. This can make the analysis of samples containing large amounts of iron, like steel, difficult as it can result in overlapping spectra as shown on the left. A less extreme example is the slight overlapping of copper with the primary phosphorus analysis line at wavelength 213 shown in the bottom right. Throughout this presentation, the example of copper interfering with phosphorus will be used to explain the interference correction model building process. You have several different options for dealing with spectral interferences, the first of which is choosing an alternate, clean wavelength for the element of interest. Returning to the spectra of copper interfering with phosphorus on 213, you can see that phosphorus 178 offers the ability to analyze phosphorus without the presence of copper. This will, however, not always be the case. Some elements have few analytical wavelengths, potassium and selenium for example. Finding a clean or interference-free wavelength may not be a possibility. If you are running an Avio 500, you also have the option of increasing the resolution from normal to high. Increasing the resolution will offer more space between the peaks. This may offer enough space to resolve two peaks emitting close to each other. If you have an Avio 200, you always operate in high sensitivity mode by default. Another option is to use background correction. The spectra displayed is for selenium with a clear background shift. In this instance, no correction model needs to be built, as the single point background correction will be sufficient to correct for the background shift. A single point correction for the selenium spectra shown on the previous slide was sufficient to correct for the background shift. However, this will not always be the case. A few notes on the positioning of background points with complex spectra. Background points should always be positioned near the base of the peak from the most concentrated standard. Having background points positioned far from the peak of interest will result in the interfering analytes rendering the background correction ineffective. Shown on the left is an example of overcorrection. The background point is positioned on a nearby interfering peak. The center spectra shows the same spectra with only a single point correction. The correction point on the left of the spectra was removed in an attempt to avoid the nearby interference. This led to an undercorrection as the background correction line, the dashed line, is not indicative of the baseline of the peak of interest. The right spectra displays an appropriate background correction. Finally, you have the option to use fewer points per peak, which shrinks the integration area. In the spectra displayed, the orange boxes indicate the number of points per peak, and the white area centered on the cursor is a visual representation of the peak integration area. Typically, at least 2 points per peak are recommended to encompass the entire area of the analytical peak. In these spectral windows shown, the white area centered on the cursor is a visual representation of the integration area. Increasing the points per peak will widen the integration area. If too many points are added, the integration area may extend beyond the actual analytical peak. If there are significant background features around the peak, the signal-to-noise ratio can be degraded. The top phosphorus spectra displayed was acquired with an Avio 200 with 7 points per peak, and the bottom shows the same spectra with a reduced integration area of 5 points per peak. You can see that with the enlarged integration area, features of the copper spectra are being included in the integration for phosphorus. This will lead to inaccuracy. Reducing the number of points per peak reduces the effect of the nearby copper interfering peak on the integration of the phosphorus peak of interest. If you are unable to resolve your peak of interest from nearby interferences using the options described, then it is time to consider a correction model. With Perkin-Elmer ICP-OES instruments, there are two options for interference correction models: Interelement correction factors, IEC, or Multicomponent Spectral Fitting, MSF. Interelement correction factors are the classic correction technique which create a mathematical correction factor which is then applied to the sample analysis to correct for spectral overlap. If you find yourself in a regulated environment, IEC is generally acceptable. Determined IEC correction factors are highly dependent on plasma and sample uptake conditions. The plasma and sample uptake conditions must remain constant. Also, prior to determining IECs, background points and integration areas must be correctly positioned. IECs will need to be recalculated in the case of any changes. Multi-component spectral fitting is a superior correction technique which is exclusive to Perkin-Elmer. The ICP-OES software uses blank, clean analyte, and mixed interference matrix solutions to build a linear least squares fit model based on Kalman filtering to correct for spectral overlap. MSF has the unique ability of uncovering low-level signals that are buried in complex matrices. MSF models are simple to develop, easy to use, and are extremely robust. Unlike IEC, MSF models are independent of concentration, plasma condition, and matrix. Only the peak shapes need to remain constant. Also, when using MSF models, background correction points are not needed as the MSF model corrects for the background. This eliminates the possible error of setting background points in complex matrices. Shown pictorially, the MSF linear least squares fit model based on Kalman filtering corrects for spectral overlap by essentially mathematically subtracting out the interfering spectra. Shown on the left is the spectra for the analysis of indium in a matrix of tungsten and molybdenum. The spectra of interest is the solid line and the interference are dashed lines. Shown on the right is the spectra after the MSF model was applied, showing only a clean spectra for indium. MSF has the unique ability of uncovering low-level signals that are buried in complex matrices. So, should you build an IEC or an MSF correction model? There are two types of spectral overlap: direct spectral overlap shown on the left, or partial spectral overlap shown on the right. Determining which type of spectral overlap you are facing will determine the correction model that should be employed. For the correction of direct spectral overlap, such as the platinum chrome spectra displayed, IEC must be used. IEC is the only correction model that is capable of overcoming direct spectral overlap. For partial spectral overlap situations, such as the cadmium arsenic spectra shown, IEC could be used, but MSF is the recommended choice. The use of MSF is recommended when possible over IEC because MSF models are independent of concentration, plasma conditions, and matrix effects, making the MSF models much more robust. How to build an MSF model in Syngistics. The first step in building an MSF model is running an acid matrix match blank solution, then a clean single element standard for each interfering element as well as the element of interest, and finally the mixed interference sample which contains the analytes of interest and the interferences must be analyzed. It sounds complicated, but it isn't. For example, let's say that you are interested in the analysis of low-level selenium present in an iron solution that has been prepared in 5% nitric acid. To create your MSF model, you would need to run a 5% nitric acid blank, an iron single element standard, a single element selenium standard, and your prepared analytical sample. For best results, the concentrations of the single element samples should somewhat mimic the concentrations found in your analytical samples. It is also recommended that this data be saved in a dedicated data set. Once all the blanks, single element standards, and samples are run, you will need to open the MSF Model Builder within the Examine window and assign the spectral profiles. Then it is as simple as saving the model and implementing it in your instrumental method. Once all the necessary blank, single element standards and sample have been analyzed, you will need to open the MSF Model Builder. There are two ways to do so. The first is to navigate the analysis ribbon and click on the MSF icon shown along the top. The other option, shown along the bottom, is to open the Examine window from the Results ribbon, navigate to the Examine drop-down menu, and select MSF. Once the MSF Model Builder is open, follow the data selection wizard to your dedicated dataset. Now that your dedicated dataset has been loaded into the Examine window MSF Builder, we must identify the blank spectrum, the spectra of the analyte of interest, and the spectra of the interferences. Select the appropriate spectrum from the list in the top right-hand corner. Navigate to the MSF drop-down and select the appropriate designation. On the screen capture shown, the blank spectra is selected on the right hand, so blank is chosen from the drop-down. Repeat the process for the blank and all standards and samples run. Blank will be the matrix match blank, analyte, the single element standard of your analyte of interest, and interference, the single element standard for the interference. When assigning designations, there should only be one blank and one analyte, but there may be multiple interferences. You will need to repeat the process of identifying the blank, analyte, and interference for each wavelength in the instrumental method. Note that the designation for analyte and interference will change from wavelength to wavelength. You will need to repeat the process of identifying the blank, analyte, and interference for each wavelength in the method. Note that the designation for analyte interference will change from wavelength to wavelength. For the example that I've been using, there's only two wavelengths in my method. One for the analyte of interest, phosphorus, which is a copper interferent, and another interference-free wavelength for copper. So, what happens with the interference-free copper spectra? Only the blank spectrum and analyte spectrum are identified. The method analyte of interest is phosphorus. However, since we are looking at the copper wavelength, the copper will be identified as the analyte. Since there are no interferences will be identified. Once you have identified the blank and analyte for each wavelength, as well as any applicable interferences, your MSF model is built. All that's left to do is save and implement the model. Save the model by navigating the Analysis ribbon and selecting the caret under the MSF button. This will open the drop-down menu to save the model. Make sure to give it a descriptive name. For this example, I named the newly created model MSF PNCU with the date it was made. Then open the method editor and implement the model by navigating to Process and then the MSF drop-down as shown on the left. Select the newly created model. Finally, return to the peak processing screen and select MSF as the peak algorithm for all analytes that need MSF collection, shown on the right. MSF should not be selected universally for all analytes in the method. In the case of this example, that means selecting a peak algorithm of MSF for phosphorus and leaving the rest as normal peak area. Save the updated method, and then you're ready to reprocess your data or run your analytical samples. Now that you have built and deployed your MSF model, you will want to verify its effectiveness. You do so by running two solutions as samples with your method containing your MSF freshly calibrated. The solution that contains only the interfering elements should not contain the analytes of interest and should return near zero values. The solution which contains both the analytes of interest and the interfering analytes should return acceptable recoveries, usually plus or minus 10% for the analytes of interest. If you have a standard reference material, this would be a good time to analyze and calculate your percent recovery. For the example of phosphorus in the presence of copper, this would mean measuring the copper single element standard on the phosphorus wavelength. This should return a near zero value. And then analyzing a sample with copper and a known amount of phosphorus, which should return an acceptable recovery. Let's take a look at another example of using MSF, this time from a published Perkin Elmer application note titled Using Multicomponent Spectral Fitting to Resolve Difficult Interferences and Metallurgical Samples using the Avio 500 ICP-OES. For the determination of trace elements in metallurgical matrices, ICP-OES is a commonly used technique due to its ability to handle high levels of dissolved solids without the need for special sample introduction components or matrix separation schemes. The significance is that sample preparation does not have to involve large dilution factors, meaning that analyte levels introduced to the instrument are not greatly affected by dilutions. Despite this advantage, the analysis of trace metals in metallurgical matrices also presents a challenge for ICP-OES spectral interferences. As I have mentioned, many elements have a large number of emission lines, which increases the potential for spectral interferences. This effect is compounded in metallurgical samples, where the matrix elements are present at high levels due to the minimal dilutions used. While several methodologies exist to deal with spectral interferences, Perkin Elmer's exclusive MSF modeling is the most robust and easiest to work with. The sample for this application note was a simulated steel digest composed of high levels of iron, chrome, and nickel in 16% aqua regia as shown. This solution was then analyzed without dilution. Measurements were made against external matrix match calibration standards prepared in 16% aqua regia using yttrium as an internal standard. The MSF model was created using 2% nitric as a blank, 0.1 ppm of the analytes of interest in 2% nitric, and by replicating the simulated steel digest matrix as the mixed matrix interference solution. All analyses were performed using an Avio 500 ICP-OES with Syngistics for ICP software. Specific instrumental parameters are shown. The analytes and wavelengths utilized are also shown. The standard sample introduction system was used, incorporating a sea-spray nebulizer for enhanced sensitivity and compatibility with high matrix samples. All analyses were performed in axial mode using the Avio 500. The power of MSF in resolving interferences can clearly be seen when looking at zirconium at 343 nanometers shown. The spectra of the matrix blank yellow, the matrix blank plus 20 ppm spike blue, sample green, and 100 ppm zirconium and 2% nitric pink are shown. There is little difference in the spectra of the matrix blank, the spike, and the sample, both in peak shape and intensity. However, the peak shape of the zirconium peak without the matrix pink differs from the peak shape of the other three spectra. This difference in peak shape indicates the presence of an interference originating from the matrix. Upon closer inspection, iron has an emission line very close to zirconium, which distorts the peak originating from the matrix. From the spectra shown, it appears that zirconium cannot be accurately measured in the presence of iron. However, by applying MSF, the interfering peaks are removed and the zirconium peak is clearly seen. On the left-hand side of the screen, the blue spectrum is the sample without MSF applied, while the pink spectrum results from the application of MSF. To confirm that the peak in the pink spectrum is really zirconium, the sample was spiked with additional zirconium and analyzed again with MSF applied. As seen on the right, the pink peak is larger, confirming the presence of the additional spiked-in zirconium. With the MSF model established and applied, the sample was analyzed along with a 100 ppm analyte spike. The results shown indicated that all spike recoveries are within 10% of the true values, showing accurate results. The work demonstrated by this application has shown the ability of Perkin-Elmer's Avio 500 ICP-OES to resolve challenging interferences in a metallurgical sample using multi-component spectral fitting. Taking advantage of MSF allows samples to be analyzed in normal resolution mode, thereby not losing intensity at the expense of resolution. With metallurgical samples, there are a limited number of matrix components, but they are present at high levels, which lead to numerous spectral interferences. By applying MSF, most interferences can be resolved, making MSF a valuable tool for the analysis of impurities in metals and alloys. We have now discussed the power of MSF models and how to create and implement them in your method. Returning to the slide from earlier, what if you have a direct spectral overlap and cannot employ the power of MSF? Interelement correction models must then be used. Let's discuss how to build an IEC model. Interelement correction factors are the classic correction technique, which creates a mathematical correction factor which is then applied to the sample analysis to correct for the spectral overlap. How to build an IEC model. Just like with MSF model building, the first step to build an IEC model is running a matrix match blank solution, then a clean single element standard for each interfering element as well as the element of interest, and finally a mixed interference sample containing the analytes of interest and the interferences. Unlike the MSF model, once all these samples and standards have been analyzed, you will need to set background points and integration areas in the examine window. The success of your IEC model is going to be heavily dependent on the positioning of the background points and integration areas. Also, remember that IEC correction factors are highly dependent on plasma and sample uptake conditions. You must run your blank and single element standards using the sample introduction conditions you plan to use for the analysis. Returning to the example of trying to analyze for phosphorus in the presence of copper, I constructed an instrumental method which contained the phosphorus wavelength as well as an interference-free copper wavelength, an acid matrix match blank, a phosphorus single element standard, a single element copper standard, and the mixed phosphorus copper sample were analyzed. Using the examine window, appropriate background correction points and integration areas were then set. With the integration areas set and the background points placed, the data was then reprocessed and given a unique name. Once the blank single element standards and mixed sample have been reprocessed to include the spectral updates made in the examine window, you are ready to open the IEC model builder. In Simplified software, you do so by navigating to the Analysis ribbon, clicking the down caret under IEC and selecting New. If the IEC Builder window does not open automatically, you will need to click the IEC button itself. The IEC Model Builder opens to the Setup tab. The results data set is where you will load into the model the corrected, reprocessed data set that you have created. This is why it is important to separate the reprocessed data into a new dataset. When the dataset is loaded, the method used to acquire that data will automatically populate in the method used to collect data box. It is very important that you use the reprocessed data with the background points and integration areas set correctly. Otherwise, incorrect IEC factors will be generated. You may fill in remarks if you wish, or leave it blank. I tend to propagate the remarks box with the date the model was created, as it will need to be periodically redone. IEC models are only valid if the sample introduction parameters do not change. The next tab is Set Limits. You can specify a minimum concentration for the correction for the IEC. Below this threshold, the IEC correction will be disabled. The Set Limits tab is used to create a filter to eliminate the propagation of random noise into IEC calculations. This field can be left blank if you wish, but should generally be set to a practical quantitation limit for the analytes of interest. The next tab is Calculate Factors. This is where the IEC correction factors are generated. Click Select Samples and a dialog box will pop up containing all of the samples within the dataset identified on the Setup tab. Select the single element interference standard. For the example of phosphorus in the presence of copper, that interferent would be the copper single element standard, which I have named 100 Cu. After the interference solution is selected, you then need to select the interfering analyte in that solution. This is the step that is sometimes confusing. For the single element copper standard, I need to select that copper is the interfering analyte. For example, even though I have named the solution 100 Cu, I still need to tell the software that copper is the interferent present in the solution. The name 100 Cu does not convey that information to the software. After selecting the interfering analyte, the actual and apparent concentrations will be generated. From this data, Syngistics will automatically calculate the IEC factor. The top menu, labeled as Analyte Interfered With, can be scrolled to see the IEC built for each wavelength present in the method. Here it has been scrolled to the element of interest in our example, phosphorus. Going from left to right, you can see that we selected 100 Cu as our sample, selected copper 224 nanometers as the interfering analyte. From this data, Syngistics pulled the actual concentration of the interference, which was entered into the method, calculated the apparent analyte concentration, which was 2.54 milligrams per liter. What this means is that despite there being no phosphorus present in the 100 Cu interference solution, Syngistics found 2.54 milligram per liter of phosphorus. From this data, an IEC factor of 25.169 was calculated. The final screen in the IEC model builder is Summarize Factors. It displays the calculated IEC correction factors for each wavelength. You have the choice of displaying all the analytes or displaying only non-zero factors. In this example, only non-zero factors are displayed. You can directly edit the correction factors in each of the cells of this table. This may be necessary if false correction values are observed. This may occur when there is a contamination of the interference solution with the analyte. Be careful to not set corrections of one element on itself. This can occur when there are two wavelengths in the method for one element. For example, if there was more than one copper wavelength in the method, it would appear in this table above the 4 phosphorus lines. You would need to manually set the IEC factor of that second copper line to 0. You should also examine your summary table for negative IEC factors. Negative IEC factors occur when the interfering peak is at the background correction position or when there is a sloping background. If you experience a negative factor, you should adjust the background correction to minimize or eliminate the negative IEC factor. Now that our IEC model is built, it must be saved and implemented in your method. To save the model, navigate to the caret under the IEC button and select Save As. It is important to give the IEC model you built a descriptive name. Names like IEC1 will not be helpful in the future. The final step in IEC model building is to insert the created model into your method. Navigate to the method editor and load your analytical method and navigate to the process screen. Here you will need to select the IEC model you built, shown on the left. Once you have entered the IEC model into the method, apply it to the applicable elements by selecting IEC in the overlap correction column. It is important that you only apply the IEC model to the elements that need it. Do not apply it universally. It is also important that you do not apply it to the interfering analyte. For our example, the IEC model is applied to phosphorus 214 and nothing else. Save your modified method. You are now ready to analyze samples using your IEC model. Now that you have built and deployed your IEC model, you will want to verify its effectiveness, just like with the MSF model. You do so by running 2 solutions as samples with your method containing your IEC freshly calibrated. The solution that contains only the interfering elements should not contain the analytes of interest and should return near 0 values. The solution which contains both the analyte of interest and the interfering analytes should return an acceptable recovery, usually plus or minus 10%. If you have a standard reference material, this would be a good time to analyze it and calculate your percent recovery. One other note about testing your IEC model: if you find yourself in a regulated environment, such as a lab that is operating under EPA 200.7, you will need to test your interference correction as outlined in that regulation. In the case of 200.7, that means running spectral interference check solutions. Let's take a moment to recap some correction model tips. The first of which is do not use a correction model unless necessary. Try to resolve the analyte of interest from its interferences using an interference-free wavelength, or improve the background point positioning, or decrease the integration area. Cleanliness is important. Make sure that you are using the correct type of acids and deionized water. Some interference issues can be resolved by simply eliminating the source of the interferent through obtaining cleaner reagents. In the case of either MSF or IEC, your instrumental method must contain both the analytes of interest and interference-free wavelengths for the interfering analytes. Finally, remember that IEC models only work if the sample introduction system and plasma parameters remain constant. Due to variations, over time, IEC models will need to be occasionally redone. For MSF, only the peak shape needs to remain constant, meaning that MSF is much more robust. Remember, MSF is far superior correction model for partial overlap spectral interferences and is exclusive to Perkin and Elmer. Thank you for your time and attention. We'll now open up the floor to questions.
Well, thank you very much. That was a great presentation there. Let's just switch over. Okay, so I guess we will get on to some questions. Just so everyone knows, you still have the ability to input questions, and we'll start reviewing them now. So, all right, Brady, are you there? Just want to double check your audio is good. So, all right. So we have first question here. Should you ever have to remake an MSF model? That's a pretty good question.
So not regularly. The only thing that needs to be constant with MSF models is the peak shape. So as long as the peak shape is not changing drastically, you should not need to redo the model.
Yes. Right. Yeah. So they're pretty stable. Sometimes I've seen them need to be redone if service has been done to the system, optics have been realigned or readjusted for some reason. That could affect the peak shape, how the peaks are, the light is projected onto the detector. Next question. Can MSF be used if you have multiple analytes of interest and multiple interfering elements, some of which are also analytes of interest?
Yeah, sure. So that's kind of the part of MSF that can sometimes be a little confusing. Whatever wavelength you are sitting in when you're in the examine window is your analyte, and the others are interferences. So it's just a matter of identifying them correctly within the examine window.
Yeah, exactly. So that's where MSF I find really shines when it's a non-direct overlap and it's a very structured background, i.e. there's multiple interfering peaks nearby that can affect with background correction, or it could be hard to do inter-element corrections properly on. That's where MSF really does a good job in those structured background scenarios. So this is a good question too. Our lab performs oil analysis. I guess it doesn't really matter what type of analysis. So our calibrations have 23 elements. In order to perform MSF, do we need to use single element standards for each element of interest?
And each interfering analyte. But when you say you're analyzing for 23 elements, all 23 of those elements are not going to have spectral interferences, but you will need them for each one that does.
Correct. So my approach when you're approaching any sample matrix sample type is through kind of knowledge of that sample type, you look at what are the potential analytes that are going to be high in concentration that are potentially going to interfere with my analytes of interest. So yeah, it's good to do single element standards of all your analytes of interest and any potential interferences. So really look at what's going to be high in the samples, and that's kind of a good place to start. And then when you're reviewing your data, looking at reference materials, so forth, look for peaks that shouldn't be there, right? Look for those interferences and try to identify what that is through our wavelength identification tools in the software, and then run a single element of that element to determine if correction is needed and what type of correction.
That's just another example where MSF would be great, because though that sounds like a lot of work you have to do up front, but it's kind of a one-time thing. You will not need to do it regularly.
Yeah, it makes life easier. It saves a lot of time for sure. If you can correct for it in that manner, for sure. And then versus IEC, where you have to run that element, you have to look at that element regularly. So there's I guess a follow-up question to that is to one of those. Is there an example you can show us that has multiple analytes of interest, multiple interferences? I don't think we have that handy, but that I think could be very useful for another webinar. Kind of get into a little bit more complex spectra. Next question. Our lab is currently using WinLab software. Does this software also have IEC and MSF model building capability?
So building models for ICs and MSF is more or less exactly the same in WinLab. You just get to the model builders a little differently. So in Syngistics, they kind of eliminated all drop-down menus, and instead we have ribbons across the top of the software. In WinLab, you'll find the model builders in the drop-down menus.
Correct. Yep. But all the functionalities still there.
Yep, the model builders are exactly the same.
Yeah, it's been around for many years now, actually. Next question. Is it not a good idea to use MSF as a standard correction technique for all elements to get better detection limits and eliminate random noise? Just identifying blank and analyte only.
So you only want to use a correction equation as a last resort when you cannot get an appropriate result using other means that we discussed. Correction equations are kind of the last resort options.
Yeah, I mean, yeah, I've seen, you know, kind of following up on the MSF thing where you're just identifying a blank and an analyte. I have seen that been used. You got to be a little bit careful. Just it does a really good job of removing that background spectra and reducing background noise. So you get some really good detection limits. Just some, if you have a very consistent matrix, it works well. You know that there's not going to be an interfering peak. You just got to watch out sometimes for interferences that are random. Like some environmental samples, once in a while you get this strange sample that'll come along and could affect that result. So you should always be on the lookout there. But yeah, MSF does a pretty good job of reducing the background noise, even if you just identify a blank and analyte spectrum. What is the typical amount of overlap that separates an IEC only correction from one that could be handled by MSF? That's a good question.
So with IEC can correct for either partial overlap or direct overlap. So if you end up with like a peak that kind of looks like an M, that would be a partial overlap. So that's a case where you could use MSF or IEC. If you have a partial overlap, so you basically in your spectra are seeing a single peak that it contains two elements, then you need to use the IEC. Kind of if there's any semblance of there being two peaks, like any kind of like M shape, then MSF should work.
Yeah, and that's and really kind of what Brady talked about in the presentation. Just try it. You know, do your background correction, background point correction. Then run your IEC, run your MSF, and compare the results. See what makes sense. See what works better for your matrix, so for your quality control solutions, for your sample. Right. So do the experiment. Check it out. Are there any extra steps that need to be taken when utilizing both IEC and MSF in a multi-element scan?
So you can use both IEC and MSF in a single method, but you need to make sure that you're not using both correction equations on a single wavelength, if that makes sense. So you can, when you're going to your method to specify either the overlap correction or the integration as MSF, you can only pick one. You want to make sure that you're not applying MSF and IECs to the same spectra, or you'll be kind of doubly correcting for your overlap.
Yep. Yeah. So yeah, usually it's one or the other. You don't want to be doing both on one wavelength. That's a good point. Next question. What are the main adjustments to remove negative IEC correction factor?
So negative factors with IEC is probably your background point positioning. So you'd want to go in through your examine window and reposition your background points.
That's it. Yep. That's what I do. If I have a really negative factor, I go back into my spectra, adjust my background point, and reprocess my factors to reduce the negativity of that, to reduce the absolute value of that correction factor to the best I can. You may need to get rid of, so if there are two background correction points, you may need to just get rid of one and use one in some cases, in quite a few cases actually. So can the Avio 200 use IEC and MSF, or is it only the Avio 500?
You can absolutely do it on both Avios. The software is the same.
Exactly, and spectra is spectra, right?
Yeah.
So so it's how it's dealing with that spectra. It doesn't matter. what sort of detector or anything. Okay, and I know we're past the hour, but we've got a lot of good questions here. So those of you can stick on, please do. Matrices like lubricating oils, while matrix may contain more than one element interference, you need to do analysis of every element overall. I kind of get that it's phrased a little strange. So in any matrix where there's a constant background, like oils, where there's a constant carbon, emissions and molecular emissions. Yeah, and it also could contain other interferences. Your blank is correcting for that matrix background. So the matrix itself is inducing spectral background. It's creating a background that could be wavy, could be noisy. By applying the correct blank to the MSF model, MSF can correct for that.
You definitely want your matrix blank to have the organic solvents in it. So running like a 2% nitric acid blank is not going to do you any good if you're running solvent-based samples. Most of the time when we do oils, they're diluted in kerosene. So you definitely want to make sure your blank has kerosene in it.
Yeah, try and matrix match as close as possible. It really helps. When making an MSF model with multiple interference, will the model negatively affect results if some samples have some, but not all interference? That's a good question.
So it should not, and you could verify that kind of the way we discussed by running standards and blanks after you get your model set up.
Yeah, it shouldn't. So especially with MSF, IEC kind of always applies the correction if the interference is present over a certain concentration, it'll apply it, right? Or and so, but MSF actually is a deconvolution algorithm that tries to ascertain if that interferent is present or not. So if it doesn't think that the interferent is present by the deconvolution routine, it won't apply that correction model for that particular interference, if that makes sense. Question not really on IECs or MSF. Someone's asking what could be the case for intensities going down.
About a million things.
Yeah, there could be a whole bunch of things. Nebulizer blockage, pumping issues, injector blockage, something's dirty. Yeah, there's definitely, I'd reach out to us for specific questions on your system. This is an interesting question. If the spike recovery on the high matrix samples come out to be well within my range, could I get away from doing any correction? Should this monitoring suffice? I think essentially they're saying if my recovery is doing well in this matrix, I don't need to do a correction. Yeah, that's right. I mean, if you're getting the right number in whatever matrix you're running, you shouldn't need to do a correction. But you should, visually look at your spectra to verify. You can usually see, if there's an issue, and if therefore if your spike recovery is also coming in where it should be, the appropriate range, then then you don't need to do a correction. Correction is really only to correct, as Brady kind of said. Don't do unnecessary corrections if you don't have to. What are the common causes for peak shape changes over the course of a run?
So the first thing that I would think would be matrix effect. So your calibration standard matrix is a little different than your sample matrix, and so the shape's a little different, and there's an interferent present that you weren't expecting, so the shape's a little different. Kind of all about matrix matching.
Yeah, exactly. Another question. on can this be used on up to 8,000? Yeah, it can be used on any Perkin, Elmer, ICP.
Yep.
Application notes, FYI, there's some handouts here. People were asking about some of these application notes and information on MSF. There's some information in these handouts here. And again, you can reach out to us. Also, if you have the software, you can hit F1 in the software and it'll give you some information. When you're in the MSF screen or the IEC model builder, hit F1, look in your help menu in the software. It actually provides quite a bit of information in the active help menu. Kind of another follow-up question from someone: can you use MSF and IEC together in a single method? I think Brady answered that. Yep, you can. You just want to, figure out which correction works for that particular wavelength in that particular matrix. Here's an interesting question. What would be considered a big negative in IEC? They caught my language there of saying if I see a large negative. I personally look at factors in our software where it's PPV over PPM of 1 or greater. I look for double digits. So if I'm 5, 6, or even 10, 20, 30, if I see very large negative, if they're fractions like 0.1 or 0.2, they're less negative. That's not as big of a correction, right? So, but it's all also depends on the level of that interference I expect to be potentially in my samples. So there's a few factors, and it's somewhat subjective of a statement, but yeah, I ideally the IEC factors are as small as possible, right? The less correction you're doing on data, the less error propagates. One last question here, and then I have to go. Is the front end plasma source similar with the Perkin Elmer ICP-MS? Brady, do you want to?
So similar, yes. The same, no. The ICP-MS has a different generator, so it's a little different.
Yeah. ICP-MS and ICP-OES RF generators are argon-based, RF plasmas. However, how they're electrically coupled are different. So yeah, it's definitely slightly different. Well, just wanted to remind everybody that our next webinar that I currently have scheduled is on December 2nd. There's actually a couple that are in the works. They might go in between now and then. Busy November for us for various virtual meetings and so forth. Check out our website for more information there. You can always go to this link here and check out what's coming up next in the Atomic Spectroscopy Seminar Series. As I said, there's a couple in the pipeline, and they will go up. Also, if you go to this link, you will see all the on-demand webinars that have been produced thus far. So feel free to check it out. You'll get a copy of that in your email, a copy of that link in your email, so you don't need to actually write it down. So I just wanted to thank everybody for joining, and thank you, Brady, for presenting today. If anyone has any further questions, please contact either of us. Once you leave today's webinar, you will receive a brief survey and the presentation, and we would appreciate it if you complete that, provide your feedback. You'll also receive a follow-up email in about 24 hours with a link to view the recording of today's webinar. So on behalf of Perkin Elmer and our presenters, thank you for joining us today, and have a great rest of your day. Thanks.